course.
what we're gonna do today and talk about.
Yeah, of course. I also
Um,
had some few slides about Golang Estonia. So I guess the main important thing is like, yeah, we have some doing things for community, and if you have some desire to speak for um, Golang Estonia, then let us know. We'll be happy to uh, organize things. But anyways, so today's topic is going to be production-ready concurrency. So the main kind of idea is it's really easy to kind of mess up with concurrency, and these are practices that I've found that help avoid bunch of issues down the line. And a mandatory disclaimer as well. So it's some of these things come at the cost of performance. So you kind of need to make a conscious choice whether to kind of do it the performant way or do it the robust way that doesn't break. And of course, there are plenty of exceptions for each of those best practices that I tell you. So uh, feel free to ask about them and where to, I guess, if you have some particular case in mind. And yeah, the rough outline is kind of this way. So, of course, feel free to ask questions at any point in time. But there are the rough outline is this rules of thumb, which is kind of going over just if you don't take anything else from this talk, then just kind of if you apply these rules, you're mostly golden already. Then choosing primitives is about how to kind of select what to do with the concurrency primitives that Go provides. And of course, like finally, we'll take a look how to implement custom primitives. And yeah, if later we'll Q&A, we'll stop the stream, and if somebody has questions outside of the like Twitch stream, then we can go over those as well. Anyways, so rules of thumb. I guess the main thing that bites people is that don't have any global variables. This kind of includes every single global flag cache pool, worker pool. What else is there? Registries. They all end up complicating testing as a result. So I'm not sure whether this requires any further explanation, but yeah, it's mostly kind of it makes your life easier if you don't have them. Of course, like this might look like a really simple thing that you shouldn't do, but people tend to overuse concurrency even when it doesn't help you. So this is quite similar to some code that I saw um, in one repository. So like if you can avoid concurrency, then avoid it, and your life will be easier. You don't have to worry about that much. Except all your tests should use tparallel. Unless there's a really, really good reason why you cannot use tparallel. But this will make your test run concurrently, which means they'll run faster. And if you have this stash raised, then you'll end up also ensuring that you don't have any this global state that might end up kind of messing up your code base. Then prefer synchronous API. It's really easy to kind of convert this synchronous API to an asynchronous one. However, like doing the reverse, converting a asynchronous API to a synchronous one is more difficult. And as you can see, for example, here to properly implement this asynchronous API, you need to implement these 3 different methods instead of a single one that does only one thing. So, and if you do want to kind of start multiple things concurrently, then you can write some helpers to do that for you. We'll take a look at those later. I think this makes no questions so far. So then one of the common mistakes is that you should always know when things stop. So you should have something that waits for the coroutine to stop before you return from somewhere. Like the go keyword is really convenient, but like outside of concurrency primitives, which we'll talk about later, you shouldn't really use them directly because I've seen quite a lot of mistakes due to these. And of course, then you can also in your test check that all your coroutines have stopped. So, which is a nice benefit. If you have background things, then it makes things more difficult. Yeah. The other common mistakes is not taking care of context cancellation. So when you're writing code that needs to respond to cancellations, you need to, of course, react to when context done gets like cancelled. The main issue here is that if you have these long sleeps, then let's say it's in the path of your waiting in your code base to shut down, then you end up sleeping there, let's say a minute before your application shutdowns. This, of course, will make your tests slower or even kind of, I don't know, rolling updates slower. So having this exact understanding where and how you react to this context being cancelled or your like operation can help you like reduce load. And time sleep often also indicates problem. This is because people kind of use time sleep to patch these different logical races in their code base instead of doing some proper signaling between concurrent threads. And of course, if any operation takes, let's say, more than 50 milliseconds, which is kind of, like a reasonable amount, I guess, you should take care of checking this context error manually. So, for example, if you have a for loop of files to read, then you can like check this context error and whether it has been cancelled. Of course, here the read file, let's say if you expect there to be gigabyte files, then you would also need to handle that case as well. So instead of reading everything into memory, you would read, let's say, a megabyte and then check whether context has been cancelled. One of the things that Brian Mills has been talking about is that avoid worker pools. One of the problems with worker pools is that, let's say you start 100 workers and most of the time they sit idle and you then look at your call stack or stack trace when some panic happens. Then you have to go dig through all of these 100 or 1,000 workers that were doing nothing. You can kind of avoid these worker pools by just starting a new coroutine using some helper that limits the amount of work you can do concurrently. And there are plenty of there are also things with worker pools where the workers themselves end up allocating a bunch of memory, And since they are persistently running in the background, they never release it. So if you have this unbalanced load of for workers, then starting a new coroutine might end up using less memory as well. Does that make sense to people?
I
I
guess
guess
as we don't get any rage in chat, so I guess everybody are following right now.
yeah. I'm just pausing so but people can type if they need to. And avoid polling state as well. Usually, this ends up kind of wasting resources and compared to like signaling when something happens using channels or any other or multiple other approaches. Um, of course, there are places where you cannot do anything else than poll. For example, some if you're asking from some API that you don't control and you want to see when something changes, then you will need to kind of do this, but avoid if possible, as usual. Um, of course, since like if it's doing repeatedly this work in like and in multiple background coroutines, it ends up kind of doing bunch of needless work if the data isn't changing. So good to be aware of it. One common mistake with regards to locking is to not unlock things. So if you have an unlock or some sort of this releasing of resources, then always defer them. That way you ensure that if you add some new if statement that you don't miss that unlock. And it also makes it obvious when you're completely missing on unlock as well, because now the lock and unlock are in the same location. Yeah, and don't expose your locks. This is kind of like it's more of like isolating your concurrency primitives from outside modification. Like otherwise, people will start locking, unlocking your things, and it becomes really difficult to track down like where the lock is being held and whether there's a lock-in version now between multiple things. So yeah, like just a good habit to have. Um, and yeah, one really helpful thing to do with coroutines is to add labels to them. That will kind of significantly help you understand what's going on in the stack traces later on. There's a really nice blog post by Jana at the Raquel.org profiler labels if somebody wants to look at. And yeah, so these are kind of my rules of thumb, and usually, like, none of them are kind of a huge problem on their own, but if they accumulate, then they kind of end up causing things that could be prevented. So does now anybody have some question about these, why these rules of thumb exactly? And so yeah, I think these are like the main things. Yeah. So bprof to label coroutine performance hit. There's it's not large. I would guess around like a few hundred nanoseconds. because it kind of needs to allocate the strings, the kind of slice for the labels themselves, and then it needs to kind of set them to the coroutine, um, like coroutine meta or label information. So there's not much work uh, to them, like unless of course you're using a lot of labels at the same time and like all that stuff. But regular usage, there shouldn't be a significant performance hit. The main thing about coroutines in general is that you don't want to do only a tiny bit of work using coroutine, because then it's kind of pointless to start coroutine. So you want your coroutines to work at least like a millisecond or so to offset the cost of starting the coroutine. Um, so yeah. Okay. Now there are quite a few concurrency primitives that Go provides, or different libraries or the golang.org/x provide. So how should you choose them? This is kind of my list of order of preference. So first of all, prefer the non-concurrent code. Then sync once and golang org/x/sync packages are pretty nice things, so they don't have any significant problems. As yeah. Then if these don't fit, then think of implementing your own custom solution, or custom primitive, or searching for a library that has them. And then finally, sync mutex, which is for special cases, which is well, I'll cover that later. But yeah, there are a few cases where sync mutex is a pretty nice option. And then you have things like sync map, sync pool, sync weight group, and creating channels, starting coroutine with gofunc, sync conditionals, and atomics. Like all of these are kind of more of ways to implement your own custom solution that is robust to different bugs, I guess. The main issue with using these below ones, I'll show a few examples. So can anybody guess what's the issue here? Like what might happen in this program as a result? If I used, let's say I wrote tests for it that are concurrent, or so, any guesses? So one of the things here is that, like, as you can see here, the server has a reference to this database. I'm currently missing some code here, but so yeah, context might get cancelled. That's a good one. So oh yes, that's the main thing, because we are closing this database here before, and this coroutine is running in the background. It means that this coroutine might use this server.database when it's already closed, right? This comes because like this server run returns, let's say, this Go function is still running in the background somewhere, and then starts to using this server.database, and it's closed, and it will kind of fail in some weird way, and then you're kind of end up spending few days debugging your tests why they are flaky. So this comes back to this: you need to wait all your coroutines, right? So this is why you don't want to use cofunc in most cases directly, right? In your domain code, at least. And yeah, the other case is this R context might get cancelled. Um, if somebody is making this request here, then let's say the client goes away, but you still like this code is still this is still executing in the background. Then if this context gets cancelled, then like this, it will abort that exact server database operation. So that might not be a bug. Let's say in some cases you may want to cancel it. In other cases, you definitely want it to complete. So you need to kind of be aware at least that, oh, that might get cancelled. Yeah. Oh, any questions about this one? I guess if hope it was clear. Then I guess the second problem is let's say look at the weight group. This is a quite common mistake. So what's the mistake here? So yeah, these are good guesses. So don't add a coroutine with WG add in the main loop. Why is that a problem? Like it's doing this in the process function, so there's an add, but why is that problematic? Yeah. So uh, okay, so the workgroup add is yes the problem because these wait and the add in this coroutine are logically racing, which means that this add may never execute in the before this wait is called. So let's say if it's never like add is never called, then like this wait will just fall through, right? Because like you don't know in which order these coroutines get started. Um, so uh, yeah, and uh, and starting more coroutines than the number of calls to wait. Uh, Not quite sure what you meant by that, but okay. The other problem with the work wait group is like this scenario. I think the problem is kind of easy to see in some sense. If you if you uh, if you've hit this problem at least once. Um, but yeah, the continuous is the problem. So yeah, it's adding more, and then it will kind of stall out. Um, so this is quite common because if you add this, use the wait group add in before, and then you later somebody comes and adds this file path extension uh, case there, then the code will become wrong. Uh, and yeah, they might miss that though. This add might now need to be adjusted as well. So this is another case of where weight groups and direct cofunc end up being problematic. So yeah. Here, of course, this scenario is obvious, but if you're this function of the domain logic is your like a few hundred lines of code, then you end up losing track of these tiny things. So how do you then handle these scenarios? So one of the things you can do is implement your own primitives. So here's an example. Let's say you implement some sort of dot pending for keeping track of the coroutines that are running in the background. So, and you ensure that the server run doesn't return until you all those background coroutines have finished. That way, you ensure that since the server started those, then it will also need to wait for those coroutines, and then you can see that, oh yeah, either you ensure that your database doesn't close before the actual when it's ready to be closed, and of course it will also fail your tests if your coroutine ends up hanging for some reason. Let's say there's some sort of deadlock there and it never returns, and then that way your test will also fail because it reaches the timeout and because the server doesn't shut down. So it helps in two ways to start. Of course, you now need to handle the case of what should the code do when the server is shutting down. Should it still try to execute it, or should it discard it together? How should we respond to the client? Should we redirect them to some other service or something else? So we can do a smarter decision about these scenarios. The other really nice package is Air Group. It provides a nice way to start so those different things in background and wait for them to complete and propagate the error as well. So there are two ways to use this error group. One is to use it without context, which means that it will wait until all of them finish completely, even if one of them fails. The other scenario is where you start the coroutine you start the coroutine with a context, and then you can see this. If one of them fails, then it will end up canceling the context. So here, that on the right side, and that will in turn cancel those other coroutines that are running in the background. So if you have multiple services that need to interact, when one of them shuts down due to some failure, then you want to maybe take down the whole server as gracefully as you can. So that kind of depends on which is the right approach for you, but you can then decide. One of the problems with error group is that you don't get all the errors that happen during this shutting down, so you may want to implement your own similar device that does return all the errors. And what's the issue with mutex here? So this is one of the common issues with mutexes. So it might be harder to spot this, but one of the issues here is the performance. So, or not performance per se, but the cancellation uh, reactiveness to cancellations of some operation. So let's say this evict old items takes 1 second, and then you get like 100 requests that call this add function. Then all of them end up blocking here in the mutex, and they will wait even though maybe 50 of the requests get cancelled. So they don't react properly when the context gets cancelled. So you get this delay in yeah, the cancellation. Yeah. Um, One way to avoid this cancellation is to implement, instead of using a mutex, you make a channel that has a single item, the thing you're protecting against, and then you can wait for to get this state and also react to cancellations. Um, it's nicer to kind of wrap this in some utility so you don't, when you're writing this, let's say this cache logic, then you don't directly use the channels. But I think this is one way to handle this. So yeah, to go over them. So sync mutex, basically only use them if the operation is going to be really fast. So and not involve any major computations. And yeah, the other issue with mutexes is that if you have a lot of them, then it's easy to get them in the wrong order. And then you might kind of, you might hit a deadlock. So the lock-in version is where, let's say you have two locks. So one coroutine, two locks A and B. So one coroutine grabs lock A, then the other coroutine grabs, let's say, lock B, and then let's say the first coroutine now tries to lock B. It cannot because it's the second coroutine is holding them, and then let's say the second coroutine also tries to grab lock A, and then you have this place where neither of them can grab the next lock, and so you have this inverted lock order that kind of deadlocks these two coroutines. So you might think that the RW read-write mutex is better, but usually it's really not. Usually regular mutex is going to be faster, and if RW mutex is faster, then there probably is even a better approach that's not RW mutex. So there's so you're better off thinking of a way to avoid RW mutex. And if you hit performance problems, there's a nice Gophers Slack-channel #performance where you can ask questions what to do and how to avoid RW mutex or regular mutex if you are performance constrained. So now let's look at channels. So here we've fixed these weight groups, and so what's the problem here now? I have trouble spotting it myself already. But yeah, so here's one mistake that might happen. The work queue is not closed, so none of the workers finish. Um, and of course, this also has the worker pool issue of kind of messing up the stack traces. So yeah, so this is like the order of things how you should evaluate when to use like what, I guess. Any questions about these things? Whether RW mutex white spurs, sure. So basically, there's RW mutex needs to have has internal mechanism to kind of to only let it let the readers use it or a single writer, right? And most of the time, if you're not contented, then it's better to use a mutex because then you have less machinery that goes on inside and kind of lets the reader and writer individually to operate. If it's doing any long operations, then of course you cannot use context cancellation, which kind of has, in some sense, the same problem as mutexes. Similarly, like if there are many readers and you have this load issue, then you are better off maybe using a sync atomic and using this copy, or not sync atomic, the sync value, sorry, and using copy and write, which means that everybody can read whenever, and when the writer like changes it, then it will overwrite the previous value atomically, and so the new readers get the new value, and so you won't get this contention between the readers essentially. And yeah, and of course, yeah, there's the long. If the readers are taking lots of time, then it's going to get it's not great either. Yeah. Any other questions? I guess no. So yeah, one of my rules of thumb is that you shouldn't really use these directly. There are better ways to do things, and so yeah, there's a really nice paper on common concurrency bugs, and as well, I'll have a link later. But yeah, if there's like code that uses them, then it's usually fine. It's not yeah, the end of the world either. But yeah, like the examples I already showed, why people can easily make mistakes with them. So, what's the better way? I guess the question. So you have these different libraries that might provide a better implementation of these that avoid these footguns. But you can also write your own custom primitives. That way, you can isolate your kind of domain logic and your synchronization logic, and it will become much easier to understand the synchronization logic compared to directly using the primitives in your domain logic. Right. So a few examples, but as I said, like these are examples that you need to tailor to your own system, I guess, because there are a bunch of different trade-offs how you want to do the concurrency. So let's take a really simple example. batch processing as slice. Um, so here's an implementation for batch processing as slice, I guess. So this is how you would use it. So the second, so so the parallel function is this synchronization primitive that walks over the items in batches, and then this can be called like this parallel length items 256, and like you do the um, split this out based on low and high, and so like um, so it's kind of simplifying this, making this processing concurrent. Of course, with now with generics, you can kind of simplify it without having to uh, use this low and high. You can kind of get nicer sub slices and stuff. The also here, I didn't add any limiting for the for how many different things can be happening in the background, and this could be added here as well. Similarly, this doesn't have context cancellation, which could be added as a few potential optimizations. Any questions about it? Guess. I guess if you don't kind of follow the exact details how it's implemented, it's more about the general idea how you would implement your own concurrency primitives and different ways how you would do them. So the other case I showed in the beginning was how time.sleep is bad because it doesn't react to context cancellation. So here's a little sleep utility that reacts to context cancellation. It's nothing like it's really tiny. However, it will end up compared to writing this code inline in your domain logic compared to calling this sleep function, it's definitely easier. Then we can take, let's say, retrying with backoff as an example. So here's an rough idea how we would design some sort of API for it. We have this next that kind of waits the appropriate time, has this context for context cancellations, and has some arguments for, let's say, the how many times to retry, how much is the first sleep, and so on. This can be also written in a different way. Let's say you like this API more. So depending on your situation, one might be better than the other. So let's say if you so if you retries change, then maybe the first one is slightly better. If the retries are exactly the same, then maybe the second one is better, API wise. A common thing is to start few coroutines and then wait for them to stop. Like one really tiny function for that is like, let's say, this concurrently. And here's how you would use it. In testing concurrent code, this is like a really nice helper. And yeah. And of course, there are the questions of what should happen if one of them fails. Should all of them get cancelled, or just or should it wait for all of them to return? Similarly, should it return all of the errors or only the first one? And of course, what if one of them panics? Should the panic be caught and then propagated through the error? Should the concurrently function itself pre-panic when one of them coroutines panics, I guess? Or should it just swallow the panic, which usually isn't a good idea in the first to do? So because panic usually indicates something is pretty wrong already. And let's say you want to wait for something to complete. Here's a fence implementation. So this is kind of you might, if you don't finish kind of finish it reading it, but like the main things it um, features it has, like make sure it doesn't require a constructor. It simplifies quite a bit of code, and you will also sometimes avoid a few pointers and heap allocations and stuff. And but yeah, the main thing is that it initializes this wait channel, and once it's released, it will close the channel, and then people can monitor this release or uh, call the wait function to complete. So as an example here, there's this concurrently, like combining these two primitives gives you this code. Let's say you start three things concurrently, and two of them need to wait for the first one to complete. So you have this fence that protects from this data to be filled, and once it's filled, then the others will continue. Of course, here there it would be fine just kind of calling this get data before the concurrently part, but if there's other logic that it can happen concurrently in those different functions, then yeah, this fence might be a good option. One of the places I've used this is a task manager, or kind of like um, like process startup dependency thing. So you could specify, oh, this process needs to wait for this to complete before you can start this other one, and then you have this graph of dependencies, and which are really nice to kind of put it right together. Yeah. Then there's the case of protecting state, and this we kind of covered. First, you use this single channel with a single item to hold the state, and then you write this with function that always properly kind of ensures that the state will be protected and doesn't get leaked. So if you call it, you have this s.with that kind of exposes the state, and you can modify it, and once it returns, um, then it will be kind of nicely protected. So I guess it's somewhat similar to like synchronous annotations for some languages. But it's more of ideas how you might structure these concurrency protection things without convoluting your the channel is blocking with a buffer of 1 here. But yeah, and of course, since this now can take context, it responds to context cancellations. Yeah. So yeah, if you want to look at it again. Then quite common use case for worker pools is to limit the amount of work that can happen concurrently. But instead of implementing worker pool, you can implement a limiter that ensures that you cannot do more work than needed. Here we have a lot of different things happening. So one is that we use this channel with multiple this limit um, to keep like these tokens uh, or sending to this channel as a token or semaphore. Yeah, that's the word. Semaphore, and to ensure that we can react to context cancellations in the select here. Before we go into the select, we also check whether maybe the context has been cancelled, and we shouldn't even go into the I guess the limiting part. And then we'll use a wait group to track how many are currently working. And of course, when we finish the function, we remove the token and clear the or remove the single item from the wait group. So one thing here, I realized that it might make sense to add this limiter working before the select. Otherwise, there might be few issues. And of course, handle the um, limiter working done case in the when the context is cancelled. But I guess those issues will come out during testing. Small typo here. Or if you're, let's say, doing asynchronous processing, then this is the example um, from the start. Is you create some sort of this server bending thing that tracks your keeps track of your coroutines, and that might, for example, here you might easily pass the context that the server has to the like child coroutines that it starts. So in some sense, it's behaving similarly to Golang org/x/error group, but with some custom logic that's helpful to you. Yeah. So here's an example implementation. And here, of course, if you look at the green arrow, then that checks that whether we should start this coroutine at all, or maybe the server is shutting down or the request has been cancelled. And if you need limiting, then you can, similarly to the limiter, you can add a limiter to this thing. Yeah. So any questions about those examples? And yeah, if you go read through those, I guess the golang.org/x/sync packages, then you can find more about how they would be implemented. And other talks that I would definitely recommend is Brian C. Mills is rethinking classical concurrency patterns. That goes into, I guess, dives deeply more into the worker pools issue and different and few other cases there, and explains them more. If you're new to concurrency or writing concurrency primitives, then I definitely recommend a little book of semaphores that goes through many of these issues. And yeah, I'll post the link to the presentation in a second. And yeah, and understanding the real world concurrency bugs is a nice paper on how things can go wrong. And of course, if you have any questions, there's a best practices channel in Gopher's Slack. I think, let me see. There, this link will work directly. But then in the meantime, if anybody has questions, then feel free to ask. So here are the slides if anybody wants to look through the slides. So yeah, thank you for listening. Any advice on how to debug concurrency issues? Make your code understandable so you can keep everything in your head. Um, this might sound weird advice for debugging, but if you cannot keep in your head, you will have a bug in the concurrent part of your code, right? Aside from that, you can use logging. You can um, it's possible to write some tracing utilities that kind of just like when what happens. Of course, you have dash race for detecting race conditions, and yeah, is there anything else? Don't think there are any other use anything like general that comes to mind at least. Yes, labels for coroutines in productions are a really nice feature.